Good day and welcome back to the third part of our discussion on changes of variables in double integrals. In the previous videos we've introduced the concepts of a change of variables, a Jacobian for a change of variables, and how we can combine everything together to evaluate double integrals. In this video we're going to investigate one more common example. We would like to evaluate the double integral over the region R of x, where R is bounded by an ellipse. And remember, a change of variables becomes useful when either the integral itself is hard to evaluate, not the case here, or maybe the region of integration itself is just not convenient for us to deal with. So let's go ahead and sketch the region and see what we're dealing with. We have an ellipse given by 9x squared plus 4y squared equals 36. To maybe more easily sketch its graph and identify x and y intercepts, we would like this 36 on the right to actually be a 1. So if we divide each and every term by 36, we would have x squared over 4 plus y squared over 9 equals 1. Or maybe more conveniently, x over 2 squared plus y over 3 squared equals 1. And this implies that we'll have an ellipse whose x-intercepts are plus or minus 2, y-intercepts are plus or minus 3. So it will be a bit taller than it is wide. So roughly speaking, we have our region of integration R, and it has x-intercepts given by plus 2 and minus 2, with y-intercepts 3 and minus 3. In order to use the change of variables formula, remember we need to do two key things. Figure out what is the corresponding region of integration, and then also the Jacobian of the transformation. And one thing I'd really like to emphasize is that this elliptical region of integration is most certainly something we could handle as either a type 1 or type 2 region. You could, for example, in this middle equation, very conveniently solve for y as plus or minus a square root, which describes the top and the bottom of the ellipse. But that's not going to be all that convenient. What would be ideal would maybe be a circular region of integration. And if you want to think about how you could get a corresponding circle, this is a transformation we can come up with ourselves. If we look at the bottom line of our work, if we simply make that x over 2 a u and the y over 3 a v. So with the transformation that we can describe as being u equals x over 2 and v equals y over 3, this ellipse that bounds the outside of our region in the xy plane becomes u squared plus v squared equals 1. That is a nice circular region in the UV plane. And when it comes to evaluating double integrals, the ideal regions of integration would be things like rectangles, which we dealt with in the previous example, or circles, like the example that we currently have. Now note, this is precisely the change of variables that we started with. If you have x is equal to 2u and y is equal to 3v, that is equivalent to solving for u in terms of x or v in terms of y. So we have determined now our corresponding region of integration S, as one could check 0, 0 goes to 0, 0. So in terms of evaluating our double integral, we're starting off integrating over the elliptical region in the xy plane. It's now a double integral over this circular region S in the UV plane. And we need to do two things. Rewrite the integrand, so every x in this case, which is all we have, will be a 2u, and then we need to substitute in the absolute value of our Jacobian. So doing a quick computation, partial xy, partial uv, And looking at the original form of our transformation, we can immediately see those desired partials. So the partial of x with respect to u is 2, and with respect to v is 0. And note, if we're using just shorthand notation, we could say xu and xv. And then similarly across the bottom row, we need those partials yu and yv. And the partial of y with respect to u is 0, as it contains no u's. And the partial of y with respect to v is 3. So we multiply down the main diagonal, subtract away what we get when we multiply down the cross diagonal. And we now have our double integral to evaluate. Note, this puts us back in a familiar scenario. If we would like to evaluate the double integral over the region S, how would you recommend that we proceed? Because this is a nice circular region, symmetric about the origin, it turns out that it's convenient to describe with polar coordinates. So in polar coordinates, here we're thinking the horizontal variable u would play the role of r cosine theta. The vertical variable v plays the role of r sine theta. And in polar coordinates, we can note our r values vary between 0 and 1, as this is a circle of radius 1 centered at the origin in the uv plane. And as we go all the way around the circle, our theta values vary from 0 to 2 pi. So converting now into polar coordinates, we have a 2 times 6, which is a 12, which we can pull out front. U is r cosine theta, and du dv, remember, is r dr d theta. The r values on the inside from 0 to 1, the theta values on the outside from 0 to 2 pi. And what remains is an extremely reasonable and efficient integral for us to evaluate. It is the ideal scenario. You're integrating over a rectangle, i.e. all constants of integration, and your integrand is a function of r times a function of theta. So breaking this up into two single integrals, we would have the integral from 0 to 2 pi of cosine theta times the integral from 0 to 1 of r squared. And as a reminder, note, you can only break it up into these two single integrals when it's over a rectangle, and the function which you are integrating separates over multiplication to a function of just theta multiplied by a function of just r. And note, we really don't even need to do any evaluations, because we know if we integrate cosine theta from 0 to 2 pi, that integral itself is going to be 0. And 0 times anything gives us back 0. And I would describe this as being a very common example of a change of variables with double integrals. And the key observation I want to make is that even though we gave you the transformation in this problem, whenever we are integrating over an elliptical region, such as the case here, we could expect you to reason your way through and actually come up with this transformation on your own. And this is one of the scenarios where we would expect that you could come up with that transformation. And as usual, make sure that you're spending some time practicing the suggested problems. If you have questions, do not hesitate to reach out. In the next few videos, we will investigate several more examples involving changes of variables. So stay tuned and take care.